Hello there, I hope you are doing great. Today we are going to learn about applications of derivatives. We have learned in calculus that when y is a function of x, the derivative of y with respect to x, that is dy upon dx, measures the rate of change of y with respect to x. In economics and commerce, we have come across many such variables where one variable is a function of another variable. For example, the quantity demanded can be said to be function of price x. Supply and price, or cost and quantity demanded, are some many other such variables. Calculus helps in finding us the rate at which one quantity changes with respect to another.
Now we'll see how derivatives are used in businesses to calculate maximum profit. So here we have quantity of a good produced is defined as a function of its price P. So first step, we define the price P of the good as a function of its quantity. Next, we multiply both sides with Q because we know that price into quantity gives us total revenue. Now we know to calculate the profit, we need two things: total revenue, which we have already calculated, and total cost, which is here given. We just simply subtract total cost from total revenue to get the profit, which here is defined by pi. Now we differentiate this equation both sides with respect to q, and we put this is equal to 0 to get q is equal to 2000. Now this tells us that at producing 2000 units of the good, we'll get the maximum profit. Putting this value q in the profit equation, we get profit, maximum profit is equal to 18,000. So we saw that derivative is a very useful tool which is not only used in the field of physics and mathematics but also in the corporate world.
I am going to tell you about what can we do with the help of derivatives in the real world. Best thing is classical mechanics aka Newtonian physics. Here we try to understand how the things work, move, how objects behave when we apply forces. To understand mechanics of an object, we need to find out about its displacement, velocity, acceleration. These three fundamental quantities give us the equation of motion, and the best thing is that each quantity, that is the derivatives of the latter. Acceleration is derivation of velocity, and velocity is in turn derivation of displacement. Dx by dt equal to velocity, that is v, and when we derivate velocity with respect to time, we get acceleration, that is dv by dt equal to a. And similarly, since v is equal to dx by dt, we can put the value of v in the second equation, that is dv by dt equal to a, and thus we will get d square x upon dt square equal to a, that is our acceleration. That is the rate of change of displacement with respect to time is velocity. This fact alone makes it easy for us to understand the nature of motion.
So now you already know the applications of derivatives in the mechanical world, where we know that the derivative of displacement with respect to time gives us velocity, and the derivative of velocity with respect to time will give us acceleration of the object. And these are the fundamental rules by which we define the motion in the macroscopic world. But if we come to a literally the smallest level you can find in the world, which is the quantum level, we realize that applications of derivatives are so much more important in this world than in the macroscopic world. Like initially, when we were starting learning about quantum mechanics, we started learning about the electron. And now electron is so small that you cannot actually even define it. Okay, it is like zero dimensional thing. So what assumption the scientists made was that the electron is just a point particle. Like it is a point, it is fixed point, it is zero dimensional, and nothing can more be done. And with this assumption, we explained everything, like the nucleus, the orbits, the atoms, the combination of atoms, and everything. But when we advanced in the technological world, we realized something that shook the world, which was the string theory, as you know, the theory of everything which was considered. But the main problem was that with the theory, that the maths worked out pretty well, but its application couldn't. We realized that making making gravitons compatible with gluons was not an easy thing. Okay, and that is basically a string theory, in which maths also works out. But we realize that there is a big problem. Like, we cannot actually do this kind of stuff. So scientists went back and found out where they went wrong. And actually, it was the first point that the electron is a dot. That assumption was wrong. Actually, electron is actually a function of wave. Now, yes, electron is defined now as a wave, which was defined by Erwin Schrödinger in like 100 years ago. Okay, and he described this thing, like, which we called as like the basic, the most basic equation, Schrodinger's equation, which is actually the partial derivative of the wave function of electron in all the three axes where actually the world is in the three axes. And apparently there is also a constant. We don't need to worry about this constant. It is just a big constant. We don't have to worry about it much. Now, if you look at this equation carefully, it is nothing but just a second order partial derivative equation, like literally the partial derivative equation, which is the most basic equation which described the modern physics. Now, this is a derivative, a second order derivative equation. Now, you know that derivatives are important in quantum.
Physics makes particular use of calculus. All concepts in classical mechanics and electromagnetism are related to calculus. The mass of an object of known density, the moment of inertia of objects, as well as the total energy of an object within a conservative field can be found by the use of calculus. The physics principles we use to derive equations which are too complicated can be easily approximated by an extended branch of calculus, Taylor's polynomials. Examples help the most, so let's jump in. One of the most relatable example is kinetic energy. We are well known with the classical physics formula of kinetic energy, that is half m naught v square, where m naught describes the mass at rest, brings rings a bell, doesn't it? On the other hand, the formula we are well aware of is the energy of particle is equals to mc squared, where c is the speed of light, but the kinetic energy would be the total energy it has minus the energy it has at the rest. You can see here. Further simplifying mass in the terms of mass at rest, we get m naught c squared upon 1 minus v by c whole square minus m naught c squared. Well, they do seem very different from each other, but they are similar. Let us see how.
Now we have the formula for kinetic energy as m naught c square into 1 upon under root 1 minus v by c whole square minus 1. Now we have taken fx as 1 upon under root 1 minus v by c whole square. Now we have one v by c as x. Now we will put x is equals to v by c, and using Taylor series we get 1 minus x whole power minus 1 by 2 is equals to f of 0 plus first derivative of x into x, then the derivative of x upon 2 factorial into x square. Then we get 1 plus x by 2 plus 3x square by 8. Now we have finally kinetic energy is equals to m naught c square into half v square by c square plus 3 by 8 v to the power 4 and c to the power 4. Then we finally get kinetic energy as half m naught v square plus 3 m naught v to the power 4 upon 8 c square.
The further we move into the series, the more closer we get to the actual value of kinetic energy that is given by m naught c square upon 1 upon under root 1 minus v by c whole square minus 1. But it would be much better if we use this kinetic energy formula rather than moving more and more into the series.